All right, strap in because today we are taking a high-speed, no-brakes tour through our cosmic backyard. We're going to break down the raw, staggering numbers of our solar system. We're talking everything from the blistering core of our local star all the way out to the freezing, dark edges of the planetary disk. The sheer scale and power of this cosmic engine we live in is it's absolutely staggering. So today, we're cutting through all the noise to bring you the raw, hard numbers. Let's dive right in.
Okay, we're starting right at the very center of it all. 27 million. That is the blistering temperature of the sun's core in Fahrenheit. At this kind of extreme heat, the immense, crushing pressure of the star's gravity keeps gaseous hydrogen and helium tightly compressed, which ignites this continuous, massive nuclear fusion reaction. This singular, violent process creates the outward pressure that actually supports the star's gigantic mass, literally keeping it from collapsing in on itself. Plus, it generates all the energy that's absolutely vital for most life here on Earth. To really wrap our heads around the solar system, we have to establish this stellar physics baseline. I mean, the sun isn't just big, it is the undisputed boss of our neighborhood. It contains almost all the matter in the entire solar system. Technically, it's classified as a G2V yellow dwarf main sequence star. Its surface gravity is a crushing 274 meters per second squared. And to put its sheer volume into perspective, the sun is roughly 100 times wider than Earth. It's even 10 times wider than Jupiter. It easily dominates everything caught in its gravitational grip. Let's cut sharply inward to the first rock from the sun. Mercury presents a really fascinating puzzle. Data retrieved by NASA's Messenger spacecraft actually reveals that despite having this disproportionately massive iron core, which takes up about 75% of the planet's radius, by the way, Mercury has a surprisingly weak, dynamo-generated magnetic field. At the equator, it registers at just 0.002 Gauss. That is roughly 1% of Earth's magnetic field strength. Pretty wild, right? Looking at Mercury's physical profile, we see a very compact world. It has a diameter of just under 5,000 kilometers. Now, because it completely lacks a substantial atmosphere to hold on to any heat, it experiences the absolute most extreme temperature swings of any planet. During the day, the surface bakes at 430 degrees Celsius. That is literally hot enough to melt lead. But step over into the night side, and with no atmosphere to trap that heat, temperatures violently plummet to a bitter minus 180 degrees Celsius. Moving one orbit outward to Venus, we hit a number that totally redefines the word extreme, 93. This is the atmospheric pressure on the surface of Venus measured in bar. That is 93 times the atmospheric pressure at sea level here on Earth. So if you were standing on Venus, the thick carbon dioxide atmosphere would squeeze you with the exact same crushing force as if you were over 3,000 feet underwater. No way you're surviving that. And that immense pressure? Yeah, it's really just the beginning. Venus actually holds the record as the hottest planet in our entire solar system. Its dense atmosphere is composed of 96.5% carbon dioxide, creating this runaway greenhouse effect that fiercely traps the sun's heat. Think of it like a supercharged, nightmare version of what we experience on Earth. This pushes the mean surface temperature to an incredibly hostile 467 degrees Celsius. Beneath those thick, opaque decks of sulfuric acid clouds lies a brutally deformed landscape. NASA's Magellan spacecraft used radar to peer straight through those clouds, and it mapped a world of just extreme volcanism. Unlike Earth, which has shifting tectonic plates, Venus has what's called a stagnant lid. Basically, it's a single, unbroken shell of crust holding in a world of extreme heat. Over 85% of this terrain is completely covered in lava flows, shield volcanoes, and towering, deformed mountain chains. So what does this all mean when we compare it to home? Well, Earth serves as the standard baseline for all the terrestrial planets. We have an equatorial diameter of over 12,000 kilometers, a staggering mass of nearly 6 septillion kilograms, and a surface gravity of 9.8 meters per second squared. Out of all the rocky inner planets, we are the absolute largest and densest. And this perfectly illustrates why Earth is the only known planet to actually sustain life. We have an atmosphere that is perfectly balanced at 78% nitrogen and 21% oxygen. We are the only solar system body with liquid water stable right there on its surface. And deep beneath us, a 5,400 degrees Celsius molten nickel iron outer core swirls around a solid inner core. That movement generates the powerful magnetosphere that actively shields our fragile atmosphere from being stripped away by the solar wind. It's an amazing system. All right, jumping further out to the red planet Mars immediately presents us with a solar system record that completely dwarfs anything we have on Earth. Olympus Mons is the largest volcano in our entire planetary neighborhood. This extinct behemoth stands a towering 21.9 kilometers high. To put that in perspective, that's nearly 3 times the height of Mount Everest. And its base is roughly 600 kilometers wide, making it just about the size of the entire state of Arizona. So how on Earth, or well, how on Mars, does a mountain get that massive? It all comes down to Mars's specific physical profile. Mars is about half the diameter of Earth, which results in a low surface gravity of just 3.7 meters per second squared. Plus, it lacks plate tectonics. The Martian crust remains entirely stationary over these hot mantle plumes. This allowed basaltic lava to just erupt and pile up in one single, stationary location for hundreds of millions of years. And because it's structurally supported by that low gravity, these megavolcanic structures could form without the crust collapsing under the weight. But hey, if you're looking for some air to breathe while you're climbing that massive mountain, you are completely out of luck. The Martian atmosphere is incredibly tenuous. The surface pressure measures just a few thousandths of Earth's. The verified gas composition is nearly 96% carbon dioxide, with little traces of argon and nitrogen. It's essentially a freezing, high-radiation, desert-like environment with a mean temperature sitting right around minus 60 degrees Celsius. All right, let's leave the rocky planets in the rearview mirror, cross the asteroid belt, and enter the realm of the gas giants. Behold Jupiter. This thing is an absolute astronomical behemoth. Just to understand its scale, mathematically speaking, you could take 1,000 Earths and comfortably swallow them all up inside Jupiter's immense volume. That is massive.
The numbers here are they're staggering. Jupiter boasts an equatorial diameter of roughly 143,000 kilometers and is over 300 times more massive than Earth. The gravity at the 1 bar atmospheric level is an intense 23.1 meters per second squared. And beneath its atmosphere, there lies a massive mantle of liquid metallic hydrogen. That's a highly compressed, electrically conductive state of matter that's just mind-blowing to think about.
Now, all that convective motion swirling inside that metallic hydrogen mantle generates the largest planetary magnetosphere in the solar system. It extends millions of kilometers out into space. But Jupiter's most famous record sits right in its outer molecular atmosphere, the Great Red Spot. This long-lived high-pressure storm system is 3.5 times the size of our entire planet, and it has literally been churning for hundreds of years. Next in line is the undeniably magnificent Saturn. We are looking at a massive equatorial diameter of over 120,000 kilometers. But notice the mass here. While it is incredibly large, Saturn has a surprisingly low mean density. In fact, at 687 kilograms per cubic meter, it is actually less dense than water. If you could somehow find a bathtub big enough, Saturn would literally float. Its surface gravity settles in right at 9.0 meters per second squared. Of course, you can't talk about Saturn without mentioning its physical and visual trademark, that brilliantly elaborate ring system. But its gravitational domain is equally impressive. The planet acts as this central hub for a massive system of natural satellites. It boasts 62 moons according to current metric fact sheets, forming a highly complex and incredibly dynamic orbital environment. Transitioning out into the deep freeze, we hit the ice giants, and the environment changes dramatically. Uranus has a diameter of roughly 51,000 kilometers and is over 14 times the mass of Earth. But here, the temperature drops violently. The mean temperature of Uranus is a bitter, bone-chilling minus 195 degrees Celsius. But honestly, the absolute wildest metric about Uranus is this, 97.8. That is the planet's obliquity, or its tilt relative to its orbit, measured in degrees. While Earth is tilted at a fairly modest 23.4 degrees, Uranus's extreme 97.8 degree tilt means this ice giant is essentially rolling around the sun, spinning entirely on its side. This leads to totally unique and extreme seasonal variations that you just don't see anywhere else. Reaching the very edge of our established planetary system, we finally arrive at Neptune. Now,
Although it has a slightly smaller diameter than Uranus, at around 49,500 kilometers, Neptune is noticeably denser and a lot more massive, clocking in at roughly 17 Earth masses. Because of this dense mass, it has a surprisingly high surface gravity of 11.0 meters per second squared. And out here, literally at the very fringes of the solar system, we hit the absolute extreme of planetary cold, -200. The mean temperature of Neptune is an astonishing -200 degrees Celsius. It is a dark, freezing, incredibly dense world that perfectly caps off the outward geographical arc of our planetary neighborhood. Wow. So we've just processed the vital statistics of our local neighborhood, going everywhere from blistering stellar fusion to the freezing dark of the ice giants. But remember, this massive, complex engine is really just one single star system in a galaxy filled with billions of them. So what other extremes are waiting out there in the dark? Well, if you're ready for more high-density verified universe data, do me a favor and hit that subscribe button right now to join us for our next explainer. Keep learning, keep focusing, and we will definitely see you next time.